Hey, welcome in. On this video, we're going to talk about The Prisoner's Dilemma, a very famous game theory example. It's going to be part of a new game theory series. If this is something that you like and you're interested in, leave a comment and let me know, and we'll try to do more of these videos. So we're going to be talking about a very specific case, a very specific story. And the story goes, there are two thieves who have tried to pull off this amazing heist. It didn't go as planned, and they were caught by the police. The police have them in two separate rooms, and they say, you can, if you confess and you give up your partner, then we're going to give you a lighter sentence. And kind of each of the thieves has the choice of whether they confess or they stay loyal and stay silent. We can formalize this with the following, 2x2 grid, or simple game, as it's kind of called in literature. So here we have the two thieves, A and B, and they each have two choices: confess and stay silent. And then we have these boxes which indicate, kind of which choice we're going to end up in. So if A stays silent and B confesses, then we end up in this box. Within each box are numbers that represents the payoff that we get, or that each of these thieves get from the cases. The bottom left number is the payoff for thief A. The top right number is the payoff for thief B. Okay, sorry, I know it's a little crooked. So let's think about a specific example, and let's actually go through the examples. If both thieves stay silent, right, they are both going to get 1 year of prison, or they're going to go to jail for 1 year. So their payoff is -1, right? And in this case, numerically, each of these players wants to maximize their payoff. They want to get the highest payoff possible. So they get -1 if they both stay silent. Now, if A stays silent, but if B confesses, then they're going to let B go free. B has a payoff of 0, which is better than -1. And A is going to go to prison for 10 years. So way worse for A. And the same thing if B stays silent and A confesses. B goes to prison for 10 years, A doesn't go to prison and gets to leave. If they both confess, if they both kind of cheat and confess on each other, then they both go to prison for 5 years. Okay? So that's the setup of the game. It's kind of intuitive. If they both just stay silent and are good, then they kind of minimize the total prison time. They each go for 1 year. If one kind of cheats and one doesn't, then one gets screwed, and et cetera, et cetera. So now I want to think about what the players are going to actually do. And in real life, there's obviously many considerations. You're thinking about, do you want to be nice? Do you want to, what's the other person going to do? What's their likelihood? Can you make a deal? Can you talk to them before? Here we're thinking about strictly rational payoff maximizing actors. So that all they care about is just these numbers. They don't care about the implication, how much they know the other person, all that stuff. They're just thinking about these numbers. So let's first think about player A. Imagine, when you're trying to decide what to do, you want to think about what the other person wants to do. So player A wants to think about okay, what if B is silent? And in that case, if B is silent, then A has two choices: confess or be silent. If A is silent, they get a payoff of -1. If A confesses, they get a payoff of 0. 0 is better than -1, so A is going to confess in that case. So I'm going to draw a little line here. A is going to confess in that case. And again, it sounds mean, right? But we're just thinking about getting the biggest possible number. So when B is silent, A is going to want to confess. What about if B confesses, right? If B confesses, A gets to choose between being silent and having -10, or confessing and having -5. So A is going to confess again. So A is always going to confess. Because we saw in both of the cases, it's going to be better off for A. Now what about B? It's going to be the same exercise, right? Thinking about what A does. So if A is silent, right, B gets a payoff of 0 if they confess, and -1 if they are silent. So B is going to confess, right? And if A confesses, then B is choosing between -5 and 10. They're going to choose -5, so B is going to confess. And you can see where these two kind of overlap is in the confess spot. So what happens in this game, and it's unfortunate, is that both players are going to confess if they are these payoff maximizing. And it's really sad, because if they both just stayed silent, then they would both get -1 instead of -5. But essentially, because of the credible threat of the other player confessing, you sort of have to confess. Because if you don't confess and they do confess and you're silent, you get -10, and that stinks. So the fact that there's a credible threat that the other player will confess means that in this game, in this setup, you kind of end up in this top left box, which is unfortunate, because it would just be better if they could just both cooperate and kind of get the -1. So the way we would parameterize this is we would say I'm just going to say CC. Sorry, it's a little bit sloppy. This is saying, let me draw this a little bit better. This is saying that A confesses and B confesses. And we would say that this is like these are the moves, and this actually is called a Nash equilibrium, and it's a concept we're going to talk about later on. But the idea here is this is the equilibrium of the game because it's the best that A can do given what B is doing. Given that B is confessing, confessing is the best thing A can do, and given that A is confessing, confessing is the best that B can do. Talk more about Nash equilibrium. What's cool is that in any finite game, there is a Nash equilibrium. There is like some equilibrium of the game. In this case, the unfortunate equilibrium is that both prisoners are going to confess. And that kind of in itself is the dilemma of the prisoner's dilemma. So hopefully that was enjoyable. Leave a comment if you liked it. Really like to see more, and I'll see you next time.